Today we're going to talk about the definitions for acids and bases, as well as conjugate acids and bases. What makes an acid and a base a base? Well, that depends on who you ask. A couple of centuries ago, we had a guy by the name of Robert Boyle, who's famous for Boyle's law and in the gas laws that we've studied. And he studied acids and bases as well and recognized that acids and bases neutralize each other and make a salt and water, but he couldn't explain how. Then in 1884, a man by the name of Svante Arrhenius came up with an idea or a theory as to how acids and bases work. He said that when in water, acids give off hydrogen ions, or H+, and bases give off OH ions. So he gave us the first practical way for studying acids and bases and explained why acids and bases neutralize each other. Now, H is often referred to as a proton, particularly in modern theory, because a hydrogen ion is just a hydrogen atom with its electron missing, which makes it just a proton. Now, back then, of course, Arrhenius didn't know what protons and neutrons and stuff were, so he just called them hydrogen ions. We have here HCl, so when it goes into water, it splits into a hydrogen ion and a chloride ion. So with this hydrogen ion, we can see that this must be an acid. NaOH has this guy right here, an OH, and it splits into Na and OH in water, so the NaOH is a base. Now, two gentlemen working independently, one in Sweden named Johann Bronsted, and another in Great Britain called Thomas Lowry, came up with another idea about acids and bases. Now, they were not working together, they were independent, but they were studying the same thing. They came to the same conclusions and published at about the same time. So credit is given to them both. These are called Bronsted-Lowry acids and bases, and their definition of an acid is pretty much the same thing. They said acids give off hydrogen ions, but by then they called them this new word, protons. So acids were proton donors. Bases were completely different from Arrhenius's definition. Protons were given off by acids, and they were accepted by bases. So acids give off hydrogens, and bases accept hydrogens. Now, this didn't contradict Arrhenius, because Arrhenius, with his OH for bases, hydroxides, well, hydroxides do accept H's to make water. So an Arrhenius acid and a base is a Bronsted acid and a base. But the difference is that Bronsted-Lowry acids and bases are larger in number. There are many things that are considered acids and bases in Bronsted-Lowry that are not considered bases in Arrhenius's definition. So things like baking soda, which act like a base but have no OHs, no hydroxides, are explained by Bronsted-Lowry theory, but not by Arrhenius. Now remember, by now we've discovered protons, and that's that newfangled word, so they called acids proton donors and bases proton acceptors. So let's take a look. We have here the ammonium ion, and the ammonium ion in water splits into an H plus ion and an NH3 molecule. Since the NH4 is giving off hydrogen atoms, or protons, it's an acid. If we look at this, we have hydrogen ions combining with NH3 to make NH4 ions, which makes the NH3 a base. So let's take a look at these two. we have HCl plus NH3 yields Cl minus and NH4. So HCl is the acid and NH3 is the base, according to Bronsted-Lowry. The reason is because the H leaves the HCl and goes to the NH3. So where it leaves from is the acid, and where it goes to is the base. If we look at this, we have the Cl and the NH4. Here the NH4 gives an H to the Cl, which makes NH4 the acid and Cl minus the base. Now, what you may have noticed is that this is the same equation written forwards and backwards. The HCl is the acid and the NH3 is the base. Here the Cl minus is the base and the NH4 is the acid. These two things are called conjugate acid-base pairs. According to Bronsted-Lowry, every acid has a conjugate base, and every base has a conjugate acid. We can figure out which one is which by just following the H. On the left side of the equation are the acids and bases. Whoever has the acid to begin with, or whoever has the hydrogen to begin with, is the acid, and who he gives it to is the base. On the other side of the equation, the one that has the hydrogen now is the new conjugate acid, and the one who used to have it but doesn't have it anymore is the conjugate base. Why is the Cl minus a conjugate base? Because it can now take a hydrogen back that it gave out before, and being able to take a hydrogen makes it a base. So if we look here, we should be able to figure out which are the conjugate acid and base pairs. We have two compounds on the left side, H2SO4 and H2O. Both of them have hydrogens at the beginning. So one of them is going to have to give to the other. But which one? Well, let's look over at our products and see who gets a hydrogen and who loses one. The hydrogen must be going from the H2SO4 to the H2O so that the left side would then look like the right side of the equation. If that's the case, if an H is going from H2SO4 to H2O, that makes the H2SO4 the acid. Since it's going to the H2O, that makes water, in this case, the base. Water can behave like an acid or a base, depending on what it's mixed with. So we have our acid and we have our base. Now remember that every acid has a conjugate base. The difference is that the conjugate base has one proton fewer, or one hydrogen fewer, than the original acid. So the HSO4 is the conjugate base. The base over here, which is the water, has a conjugate acid, and the difference between a base and its conjugate acid is one hydrogen. A base, when it becomes its own conjugate acid, gains one hydrogen. So the H3O plus ion on the right side is the conjugate acid. There are some things you need to remember when you're thinking about conjugate acid-base pairs. The first thing is that they're on opposite sides of the equation. An acid on the left will have a conjugate base on the right. A base on the left will have a conjugate acid on the right. There are always two. If there's a conjugate acid, or if there's an acid, then there's a conjugate base, and if there's a base, there's a conjugate acid. Each one, the acid and the base, have their conjugate pairs. The difference between a conjugate acid and or the difference between an acid and its conjugate base is one proton or one hydrogen ion. And the difference between a base and its conjugate acid is also only one hydrogen ion. So they only differ by that H. An acid has one more H than its conjugate base, and a base has one fewer hydrogen than its conjugate acid. The last thing to recognize is that a strong acid makes a weak conjugate base, and a weak acid makes a strong conjugate base. The reason for this is that a strong acid is very willing to give up its H, so its conjugate base is not very willing to take them back. A weak acid, it's very hard to pull the H off, and then its conjugate base very strongly wants to get it back. So if we have a strong acid, its conjugate is a weak base, and if we have a weak acid, its conjugate is a strong base. This applies to bases as well. A strong base will have a weak conjugate acid, and a weak base will have a strong conjugate acid.